my recording in progress. Okay, so it's my delight to welcome today's speaker, Professor Allison Koenecke, who is an assistant professor of information science at Cornell. Her research applies computational methods such as machine learning and causal inference to study societal inequalities in domains from online services to public health. She is regularly quoted as an expert on racial disparities in automated speech-to-text systems, and previously held a postdoctoral researcher role at Microsoft Research and received her PhD from Stanford's Institute for Computational and Mathematical Engineering. So with that, I'm going to turn it over to you, Allison. Take it away. Thanks so much.
Thanks so much for that kind intro. And let me just do the whole screen repositioning, share screen. Everyone can see this, hopefully. All right. So to start, thank you for inviting me to be here virtually. By way of introduction, I think a lot about algorithmic fairness in a bunch of different online and offline services. So a lot of my recent work in online services kind of covers things like online ads or recommendation systems or A/B experimentation in the context of heterogeneous populations and how those biases might trickle through society. And the thing I'll be talking about today is on speech-to-text systems, so also known as automated speech recognition, since it seems like the timely thing to do in the wake of everything happening in the world. And so with that, I'll get started. I'm talking about racial disparities in automated speech recognition, and a lot of this is from our PNAS paper with a bunch of fantastic folks. Couldn't have done it without this interdisciplinary team of linguists and computer scientists and mathematicians. So that's the bulk of what we'll be talking about. But I'm also going to kind of make a nod to the recent happenings that I've alluded to, right? So OpenAI now has these massive ASR models. Google is entering the ring. And so what does that really mean in terms of research and specifically auditing research pertaining to speech recognition systems? So with that, let's start by just defining this, right? So what is an automated speech recognition system? I'll be referring to these as ASRs throughout the talk. You can think of this as anything that you might interact with your voice. And so oftentimes for the average person, this might look like a physical device, right? So it might be a Google Home, it might be an Echo, it might be your phone. And these feel like pretty low stakes scenarios if there are issues, especially with regard to fairness. And, you know, if you're asking your phone to like pull up a recipe for something or asking your Echo to set a timer for something that you're cooking, right? These are fairly low stakes. But actually, these are really important to get right in the context of many other applications, right? So one example is for individuals with disabilities. These are critical to allowing them to, for example, watch videos with subtitling or interact with devices with their hands. This is really important in car systems for safer driving. And there are specific handheld devices that are used by doctors to transcribe patient notes, and these things are specifically trained on medical jargon. And a last example I'll give is in court transcription systems, right? So like usually there is a person who is a human court transcriber who writes down everything that's happening. And increasingly this is becoming an ASR driven task for cost cutting reasons, right? So there are huge repercussions here if you think about the downstream effects, right? So if the technology generating these transcriptions is biased, how is that going to affect things downstream? If all of the Black defendants on trial are disproportionately being transcribed incorrectly, is that going to lead to perpetuated inequities downstream in the actual sentencing, right? So with that context, I think ASRs are really important. And so let's talk about how we actually audit these systems. And the study I'm talking about, we audited 5 different big tech companies and their corresponding ASR systems. Each of them has a big commercial API where you can just batch transcribe a bunch of, you know, you feed in a bunch of MP3 or WAV files and it spits out a bunch of transcriptions. So to step back, we're auditing these big tech companies. Is there any precedence for this? The answer is yes, right? So a lot of you presumably have seen the Gender Shades work from Joy Buolamwini and Timnit Gebru, right? And the premise of this was actually facial recognition is really biased. And so if you look at 3 big tech companies who offer these commercial API services, you can see that performance in facial recognition is much worse, specifically for darker skinned female faces, as opposed to the other kind of intersections of faces that they study. So with this in mind, and with this as kind of the initial idea for how we would approach this, we thought, okay, why don't we try and do something similar, but thinking about speech-to-text systems, right? So the first thing we need to do is figure out where to get our data from. And this is a lot trickier than one might expect. So our data we get from sociolinguistic interviews. I'll explain what that means in a bit. But broadly, we take all of our Black speakers from something called Choral, and we take our white speakers from something called Voices of California. Now, why sociolinguistic interviews matter is because they allow us to get kind of natural simultaneous spoken speech. Spontaneous speech is what this is called in linguistics land. And this is basically where a hardworking linguistics grad student goes and has a standard slate of interview questions, and then they ask the standard slate of questions to the interviewee. And so these questions might be things like, where did your parents work when you're growing up, or what games did you play as a child, things like that. So relatively open-ended. And then the crux of what we want to get out of it, the spontaneous speech, is what the interviewee is saying. So they would respond in kind of natural form to these questions. This is important, and all of our data is from these sorts of sociolinguistic interviews, because the alternative is using this thing called read speech, which is basically you print off Wikipedia pages, and then you ask your interviewees to just read what's on Wikipedia. And while this is nice for getting that kind of acoustic difference between how people pronounce the same word, it's not giving you kind of the more natural situation of how do people naturally phrase sentences, how do people use grammar differently, that sort of thing. And so one big issue with a lot of the previous audit studies, and what oftentimes the benchmarks were previous to this, was entirely using read data. And so this is a much easier problem to solve. In general, benchmarks are very high and very good for ASR systems if you're just looking at read speech. And so we wanted to make sure that we were doing something that was a bit more reflective of the actual kind of how people interact with these systems, which is very rarely like reading from Wikipedia. So the other big thing we need to make sure we do is not test on the trained data, right? So if we know that Google and Microsoft, et cetera, are already ingesting the Choral and Voices of California data, then it's going to get really high accuracy. There's no point in actually doing this audit study. So we did have to confirm that, in fact, none of these systems were specifically training on any of these data. Part of it was private. Part of it we did actually get confirmation from these companies. So that was all squared away. And so overall, this gives us about 40 hours of speech. And the final kind of key thing that we do here is we have to make sure that we have some form of ground truth, right? Because if we don't have this form of ground truth of what these humans are actually saying, it's very hard for us to actually evaluate, are these transcriptions any good? And so the key thing here is that for all of the data that we use, all of the speech data has corresponding human-generated ground truth transcripts. And by human, I mean specifically like hardworking linguistics grad students who have actually gone through and tagged everything, not just with the words that are being said, but a bunch of other stuff like breath marks and laughter. Each of these has very specific linguistic codes. And so all of this is tagged so that we can clean it and then make sure to match those ground truths to all of these audio snippets. So what this gives us at the end is we have all of our interviewee only data because we don't care about the interviewer's canned questions. We snippet everything to 5 to 50 seconds roughly. And so this just means we're looking at natural conversational pauses. So for whenever an interviewee is speaking, we'll just start when they start speaking and stop when they stop speaking, and then the interviewer switches to speaking, that sort of thing. And then what we do is we do some propensity matching on the attributes that we have, which is just age, gender, and duration of the snippet, so how long the snippet is. And so that gives us about 2,000 matched samples between Black speakers and white speakers. And the idea here is now we have about 2,000 MP3 or WAV files of Black speakers speaking, each for 5 to 50 seconds, a corresponding matched set of white snippets. All of these MP3 files are then fed into our black box, of Apple, IBM, Google, Amazon, Microsoft, right? And so from that black box, we're getting a bunch of transcriptions. We get 5 transcriptions for each of the Black snippets. We get 5 transcriptions for each of the white snippets. But then the question is, how do you actually know if these transcriptions are accurate, right? So like, how close are they to the ground truth? How do you actually figure out a measurement for this? And the answer for the computer scientists in the room is you just calculate the edit distance. But in linguistics land, this has a different word. This is called the word error rate, or the WER. And the way you calculate this is you sum up the number of substitutions, deletions, and insertions and divide by the total number of words in the ground truth. And so to go from what a great presentation to that is a presentation, you would substitute what for that, you would delete is, and you would insert great. Sorry, go in the opposite direction. And so that would give you a word error rate of 3 out of 4. And so the question obviously is like, is this good or bad? As a reminder, these are error rates. So high word error rate, bad, low word error rate, good, right? So 75% is quite terrible. In fact, I would say that 50% is already way too high, because 50% means that every other word that's being transcribed is incorrect in some sort of way, right? So if we think about this as kind of 50% is our benchmark of like already really unintelligible, 0% is perfect transcription, matches identically to our ground truth. That's maybe the kind of range that we want to be thinking about. And the kind of headline that was then reported in a bunch of media outlets from our paper, et cetera, is this one, right? Which is that Black word error rates about doubled white word error rates that we found in our paper. And so you see that Black men, for example, have about 40% word error rate. So really, really high, really close to that 50%, almost unintelligible. Whereas white women have the most accurate transcriptions from these ASRs at less than 20% word error rate. That being said, these are still numbers. So what does this actually sound like? So I'm going to play 2 snippets for you. And each of them is chosen with a word error rate that is comparable to the average bucket's word error rate. So here I'll play a snippet of a white man. You can see the red markings are where the particular ASR got the transcription wrong. And if you sum up the deletions and insertions and so on, you'll find that this particular snippet has a word error rate of 0.2, and that's roughly comparable to the average white man's word error rate across all of our data.
Well, when I was really young, I'd had a book of basketball statistics, and I would spend a lot of time reading them. And for some reason, I forget why now, but Jason Kidd ended up being my favorite player.
All right, so that was one example. My next example is for a Black woman. You can already see that there are a lot more red markings, right? There's a higher word error rate for this ASR system on the listening to this Black woman and transcribing it. And one thing I want you to keep in mind is thinking about, do you find this to be significantly less intelligible relative to the white man's sample from before? Or do you think it makes sense that this is a full almost 10 percentage points higher word error rate?
And she had these little like snow cone things. I don't even know what it was. But it's not like the snow cones up here. Like, I don't know how to explain it. But, a bag of candy for a quarter, like a full bag of candy for a quarter.
So I think hopefully everyone kind of thinks to themselves, well, I didn't have any significant trouble understanding that. I think that's generally what people would say, right? And so the issue here is, why are we getting these significantly worse error rates? And another thing I'll mention, just to preempt the question, is that this is consistent across all the firms. So we do see on average this doubled word error rate for ASRs on Black speakers relative to white speakers. And we do see this doubling in kind of all of the 5 firms that we tested. So with that, I want to go into kind of 2 of the deep dive questions, right? So like this is the headline that I read reports on, but the actual research, I think the meat of it is in these kind of 2 sub-questions that we ask. So the first question is, how do we actually know that these are racial disparities? So can we rule out other options? And the second big question is, why are these things happening? And so that involves looking at the underlying machine learning systems, figuring out kind of if we can do some sort of analysis to parcel out where these errors come from. Okay, so to start, how do we know that these are race-based? So here's a plot. I don't know if you can see the shading, but the gray background, 3 cities on the left, are the ones that are where our Black speakers come from. So the Coral data set was collected in 3 different cities, Princeville, DC, and Rochester. And our white speakers come from Sacramento and Humboldt. So these 2 geographic areas on the right. And so a kind of obvious thing is, people who are from different areas tend to speak differently. We're aware of the different accents that exist in the United States, right? And we have some coverage of this, and that each of our Black and white speakers, we do make sure we have one location each that's a city and one location that's a bit more rural. So we have a bit of that coverage. But you might notice something funky going on here with Rochester, right? So Rochester is where our Black speakers, a subset of our Black speakers are from, but the word error rates are actually quite low. So they're quite comparable to the white speakers' word error rates across the board. And so if you just look at Rochester, it would be very hard for us to say, clearly there is racial bias here because clearly the Black speakers in Rochester are being transcribed fine, right? So in order to figure out what's going on here, we need to introduce a couple different terms. And so the first term I'll introduce is this concept of AV, or African American Vernacular English, also known as African American Language or African American English. And this is broadly a term used to distinguish how some African Americans might speak across the US. And we contrast this with the term Standard American English or Standard English, or standard, I'll try and say in quotes because it doesn't refer to actually being any sort of standard, but rather just referring to the regularization of features, grammatical features, phonological features that are used in spoken English. So broadly, we'll talk about AV and Standard American English. So AV is something that's spoken by something like 80 to 90% of African Americans, or can be spoken by 80 to 90% of African Americans in the US. And it's kind of a special sort of variety of English is what it's called, in that it isn't particularly geographic based. So whether you are an AV speaker in New York or California, the fundamental kind of rules, grammatical and phonological rules of AV are going to be about the same. So you might have some additional geographic variation in how you speak, but the actual what's going on with AV is going to be about the same. And so what we can do is actually just count the number of AV linguistic features in a set of snippets within each of our different interview sites. And so what does this mean? Well, there are some examples like the zero copula, where in quote unquote Standard American English, you might say they are gone, A-R-E. R is the copula in that sentence. So if you take away the copula, so there is zero copula, and you just say they gone, that would be the African American Vernacular English formulation of that sentence. So zero copula is one example of a grammatical feature that we might tag. Another would be things like final consonant cluster reduction. So going from band to ban, so not saying that final D syllable, D consonant, is another example of something that we would tag as a specific AV feature. And so what we can do is then listen to a few examples and then think about what this might mean. So here we can see that this has a very, very low word error rate, so almost perfect transcription. You can see there's only one red marking, so the ASR only messed up on one word of transcription. And the blue highlight is where we have our singular AV feature that was spoken as tagged in this particular snippet. And so here the example is going to be syllable initial fricative stopping, which just means that the V, the TH sound, is going to sound a bit more like a D.
Grow older, we get darker. So I was extremely light when I was a child and very skinny. And so I was like an outcast because I was made fun of because I was the white girl at the school.
Okay, so in contrast now, let's listen to something with more AV features, right? And so you can already see hopefully where I'm going with this, which is that the word error rate is super high. We have a lot of red markings for mistakes that the ASR made for this particular speaker. And we also have a lot of blue highlighting showing that the speaker is speaking with many AV features.
Well, our second grade teacher gave me the nickname Snake because she said I was sneaky, you know. I'd be sitting one place and she turned around, I'm sitting someplace else.
Okay, so you're all smart people, so you know where I'm going with this. Along the x-axis, we're plotting basically the share of words that are blue highlights, right? So the share of the words that have some AV feature, grammatical or phonological, that we've tagged. And along the y is still our word error rate. And again, high is bad, low is good. And what we see is with the more AV features that you're speaking with, the worse your transcription accuracy is going to be, right? So we see this positive correlation. And now I'm just going to show the exact same plot, but now with color. So if we actually just overlay the locations that we were looking at, remember that Rochester was our kind of big question mark before, where the word error rates were on average about 0.2, so very similar to the white speakers in our sample. And it seems like we can actually attribute a lot of this to the fact that very few of the Black speakers in Rochester are speaking with particularly many AV grammatical or phonological features. In contrast, for example, Princeville, the vast majority of our speakers are speaking with relatively high degrees of AV. And so that's where a lot of this kind of disparity is going to come in. And so we might want to say, in fact, this isn't specifically just a Black speaker versus white speaker thing. This is specifically a standard American English versus an African American English, and the degree of African American English that you speak that's causing this sort of variation that we see. So that being said, there's a lot of other work that delves a bit more into this kind of like geographic-based sort of set of differences. I will also say that Southern speakers tend to perform worse in a lot of speech-to-text systems. Scottish speakers tend to perform worse. And so there are a lot of different pockets of geographic areas where a lot more work needs to be done. And we'll talk more about that at the end of this talk. Okay, so that's kind of the sub-question part one. How do we actually know that this is race-based? And so I would still contend that given that the question is still about whether or not you use AV grammatical features or the degree to which you use AV grammatical features or phonological features, clearly there is still some racial components. So given that there are these racial disparities, why are these happening? And so in order to tease this apart, we want to think about what's going on under the hood in your average ASR system. And so in general, it has two components. It has the language model and the acoustic model. And so you can think of this as the acoustic model dealing with how you're saying something. So it's the thing taking those sound waves and translating them into a phone or a phoneme. And so that's dealing with things like inflection or how you're saying things. The language model is dealing with what you're saying. So this is the thing where it looks at the phones and says, oh, this is probably the sentence that she's trying to say. And so before I had to do a lot more explaining about language models, now I think I can just point it in and say like ChatGPT. So that's, that's what's going on there. And so what we're going to do in order to kind of tease apart what's going on here in our particular data set is do effectively a set of process of elimination. So 3 different tests to see what's going on and if we can attribute any of this kind of doubled word error rate for Black speakers to a specific issue that would be present in one of these models. So the first thing has to do with lexicon. And so the idea here is let's say in this very untrue example that all of the white speakers in our sample all have cats and they all talk about cats all the time, they love cats. Let's say that all of the Black speakers in our sample have dogs, they all talk about dogs all the time, they love dogs. However, Google, we'll pick on Google today, their speech-to-text system is only trained on white speakers historically, and so they only have knowledge of the word cat. They talk about cats all the time, they are able to correctly transcribe the word CAT, but they have no knowledge of the fact that the word dog exists because they've never been trained on the word dog. No one's gone in to edit the lexicon and say, oh, actually DOG is a word that exists. So Google just has no knowledge of this vocabulary word. So the question here is basically, can we look at the lexicon use and the lexicon shares and figure out, is it just the case that, the Black speakers on our sample are disproportionately saying a bunch of words that for some reason Google doesn't know about, right? Because none of the white speakers are saying these words. The question here, though, is, well, we're not Google internally. Of course, we can ask them and they won't give us their proprietary data of what's in their full dictionary, right? So Google's not just going to tell us what's in their lexicon. But conveniently, we did just run like 40 hours of speech through Google. And so if you just take all of the unique words of the outputs that Google generated, it's like pretty close to reconstructing a reasonable dictionary, right? It's not going to get everything, but it'll get a decent number of things. And so what we can do is then just calculate the share of words that we see for each of our Black speakers and white speakers and see if there is reasonable coverage in our kind of faux dictionary that we've created for each of these ASRs and see if there's different coverage for white speakers versus Black speakers. And the punchline is no, there's no difference. It's actually quite good in terms of lexicon and vocabulary. Things are in like the 99% range. So almost all of the words are actually in the Google lexicon and all of the other ASRs that we tested. So it seems like lexicon isn't kind of the nail in the coffin for getting this doubled word error rate. So our next test is going to be about the grammatical differences. And so for this, we have to introduce another metric. So the term here we're going to be using is perplexity. And this is basically just the number of ways that you can continue a sentence and fill in the blank. And so here our example might be the dog jumped over the blank. And if you are the ASR, if you are the language model specifically, you might think to yourself, okay, so I ran the numbers and there's like a 5% chance that the next word is fence, 2% chance the word is cup, 1% chance the word is moon. So if the next word is in fact fence, and I look at that, I would say, oh, well, actually, I personally had a really high percentage probability that I attributed to the word fence, so I'm not particularly surprised. And so given that I'm not very confused about the sentence, the dog jumped over the fence, I would have a low perplexity. Meanwhile, if the actual next word was moon, I, as the language model, would be quite confused because I thought that there was a very low chance that the next word would be moon. And so then I would have a high perplexity. So that's roughly how we're thinking about it. Perplexity is basically just how confused the language model might be. And so what we can do is just calculate the average perplexities using, at the time, this would be an older version of GPT, which was public. And so we can calculate using GPT perplexities for our African American English speakers versus our quote unquote standard English speakers. So we'll give an example with the zero copula again. So that would be things like he is a pastor versus taking out the is would be the copula. So versus he a pastor. And recall that high perplexity means that your language model is very confused, right? So we see much higher numbers for African American English speakers relative to quote unquote standard English speakers across the board for this example. And so these are just stylized examples that we input, not from our data. And this broadly kind of complies with what we might expect, right? So if we think that historically our speech-to-text systems are not trained on a lot of formulations of zero copula, then probably they're not going to do as well in terms of expecting the zero copula effect, right? So that'll seem reasonable. So the plot twist here is that this actually doesn't happen when we look at our data, right? So we have this surprising result where actually our Black speakers have lower, very slightly lower perplexity relative to the white speakers in our data. So why might this happen? One answer to that is because of the number of unique words that the Black speakers are speaking in our particular data set, right? And so if, for example, your language model is just very naive and just does a uniform guess across the set of unique vocabulary words that it thinks that you know. So let's say that Ravi is very smart and knows 5 words in his vocabulary. I know fewer words. I only know 4 words in my vocabulary, and you're a language model and you're just guessing. So the language model would have a 1 out of 5 chance of guessing Ravi's next word correctly. But it would have a bigger 1 out of 4 chance of guessing my next word correctly, right? So this sort of effect is kind of what's at play. Even if we normalize it by the number of unique words, we still kind of don't see the smoking gun with regard to perplexity as kind of this big reason for the differences that we see. So it seems like grammar isn't the big reason leading to these doubled word error rates across the board. So this leaves us with our acoustic model. So can we actually find this doubled word error rate issue? And the question here is, well, going back to this whole issue of using a sociolinguistic interview as opposed to read speech, right? If we were in fact just using read speech, we would have a much easier time measuring this because all of the words would be the same. And so we would just naturally only be measuring the acoustic model. But we decided that it would be smart to actually use spontaneous speech. And so this has like caused a big issue because now it's a little harder to test for whether or not it's just an acoustic difference, right? But conveniently, we can find people saying identical phrases in our sample because you might recall that a lot of the questions are things like, what was your mother's profession when you were growing up? And so a lot of people might respond, oh yeah, my father was an accountant and my mother was a fill in the blank of a profession here, right? So you do actually see quite a lot of overlapping n-grams, 5 to 8 word n-grams is what we've focused on. And so if you just focus on those and compare the word error rates just on those matched phrases, we can actually recover that doubled effect again. And this is just looking at those specific matched phrases. And so the kind of conclusion here is that a lot of what we see can be attributed to the acoustic models. And so to recap what our study showed, so again, first of all of the 5 ASR systems that we studied did show a decent number of disparities, especially in this kind of doubled word error rate sense of Black speakers relative to white speakers. We can then say that this is specifically due to African American vernacular English, kind of differences there, and specifically differences in the acoustic model. And so this is often things like rhythm, pitch, syllable accenting, that sort of thing, in that ASRs just don't quite understand how those sound for African American vernacular English speakers relative to quote unquote standard American English speakers. But does this mean that the language model is actually totally fine and unbiased? No, right? So it happened to be the case that in our data, we didn't see that that was kind of driving the magnitude of the errors that we were seeing overall. But there are a ton of examples of language model bias. So this paper by Martin and Tang, for example, studies the grammar of the habitual be. And so the habitual be is this idea of habitually being somewhere. So oftentimes the grammatical construct of I be somewhere might be construed as I am there currently, but actually what it refers to is habitually being somewhere. So being usually in this place. And so this is a common grammatical feature that you might find in AV speakers. And what the Martin and Tang paper found was that if you look at the word error rates of the words surrounding the habitual be, so pre and post the habitual be, as opposed to a non-habitual be, you see worse word error rates around that habitual be. And so again, kind of mirroring what we found with perplexities in our kind of stylized examples of specific linguistic features, there are definitely still instances where it's clear that certain grammatical features are causing these sorts of biases that we would see in a language model. And so also, I promised I would say something about kind of like scary things are happening in the world today. So there are also big things happening with generative AI, right? And so with LLMs, you might consider the fact that, in fact, the language models being fed into a lot of our speech-to-text systems today are increasingly using generative AI, right? So not necessarily that OpenAI's Whisper, which is their speech-to-text thing, has ChatGPT exactly underlying their models, but it's probably a similar technology, probably also generative AI. And so again, caveat, screenshots do not constitute, actual full studies of GPT, but as just an illustrative example, right, ChatGPT clearly does have the ability to figure out what sort of grammars are in African-American English, right? So here they actually give two examples. So one of them is the zero copula, so dropping the is and he is a pastor, and one of them is using a habitual be. So those are the two things that we've talked about in terms of grammar. But they're not going to say that that's grammatically accurate. In fact, this language model would say this is not grammatically accurate. And so you might imagine that a language model that doesn't think that certain types of speech are grammatically accurate aren't going to be, suggesting these modes of speech when they're trying to figure out what someone is saying verbally, right? The other kind of thing to flag is that people write in different ways. And so you can think about different ways of prompting if you're prompting ChatGPT, for example. So here again, we can talk about the habitual be. We can also throw in zero copula, our two grammatical features we've been talking about. And so if you, in fact, put in these different prompts, again, content is all the same. It's just changing two grammatical features. You end up with very different numbers of hallucinations and very different kinds of hallucinations, right? And so if you think about it, this is, the same technology that is underlying a lot of modern ASRs now. So there is this shift into using generative language models, right? So I think this is something that we really need to start worrying about and thinking more about methods to audit. And so I think, for example, looking at these sorts of grammatical differences in prompts, looking at hallucinations, that sort of thing is going to be kind of what the next few years of auditing these systems is going to entail. And so I wanted to cap off with kind of like what's going on in the world today, not just with auditing ASRs, but how ASRs are being used. And I'll start with just a call to action, right? So kind of the obvious thing here to say is, well, a lot of these issues were caused by the fact that historically speech-to-text models have been trained on only white standard American English speakers. And so we really need to collect more diverse data. And this isn't just for AV speakers, this is also for non-native English speakers. This is for speakers from different geographical regions, right? A lot more does need to be collected. And quick pitch for my fact paper from this year, which broadly thinks about guidelines for how to actually document this sort of data collection. Right now, a lot of the speech data is really poorly documented in terms of, are people's hometowns tagged, or are their linguistic features tagged? Is the ground truthing actually accurate, or have they, kind of willy-nilly written what seems like they're saying, but haven't actually considered the actual variety of English that they're speaking with? So, for example, a white transcriber might not pick up fully what the Black speaker is saying if they're speaking African-American English and the white speaker isn't familiar with transcribing African-American English, right? So big issues and lots of things to solve on just kind of the data collection, data documentation side of things. Another thing is just recognizing that this isn't just a data problem, this is also a people problem, right? And so we really need to make sure that the people throughout the pipelines who are creating these ASR systems are diverse, because then you'll be able to catch issues of fairness and bias earlier on in these pipelines. Of course, it would be great if these ASRs would just do this work themselves, do the auditing, and publicly report their progress over time. And I do think this is something that a lot of consumers are increasingly concerned about. And so doing this publicly would be a great way to also capture more customers. And lastly, I want to talk a bit about kind of what's going on in the legislative sphere, right? So a lot of progress has been made in other domains, and we'll talk a bit about the gender shades paper again, that we should really be learning from for ASRs, right? So recall gender shades, clearly bias was shown in different types of faces for facial recognition technology. And what actually ended up happening was, in the wake of the Black Lives Matter protests, this research was foundational in making sure that IBM, Amazon, and Microsoft all stopped selling their facial recognition tech to police forces. So is there something similar going on in ASRs? I'll instead just tell you some horror stories. So one big horror story is that incarcerated people are being surveilled, right? And so their phone calls are being recorded and monitored. And one way that they're being monitored is this hot new tech startup, which basically takes the phone calls, runs them all through specifically Amazon's speech-to-text system, generates a histogram of the words spoken, and then if any of the words spoken are things like gun or any sort of red flag words, suicide, things like that, decisions are then made. So for example, an incarcerated person could potentially be put in solitary confinement on the basis of Amazon thinking that they said the word gun when really in reality they were saying something like gonna, right? So all sorts of potentially terrifying things. But of course, my favorite part of this website is they say it's automated, it's fast, and it's objective because there is no implicit bias, no racial profiling, when in fact the fundamental technology that they're using in order to do this is doing this kind of racial bias work on their behalf. So that's one big concern I have. And so in the kind of court space, in general, there's a lot more to be worried about, right? So again, we talked about court reporting as one of the big use cases of ASRs these days, right? So previously there were human court transcribers. Now ASRs are increasingly being used. And in general, it's like not clear that humans are significantly better than AI in terms of being biased, right? So if someone's asking for a lawyer dog, it is like not great that a human judge then responded that in fact you would not get a lawyer because there's no such thing as a lawyer dog, right? So we know that ASRs are biased, but we also know that humans are biased. So a Jones 2019 study found that in fact human court transcribers were not able to reach the bar that was necessary. So they have to perform at least as well as a certain number on a series of tests in order to become court transcribers. And that those sets of tests are generally on kind of standard American English speakers. They consistently do not meet that bar if they're transcribing African American vernacular English speakers. And you can imagine all of the negative repercussions here. So if, for example, double negatives are being spoken, but only one of them is transcribed, that can totally invert how exactly this would be interpreted. And this was true kind of across the board for the court reporters that were studied in this particular case. So what to do? There doesn't seem to be any particularly good solution here. But I think broadly what we should be thinking about is that humans do need to work together with AI for fair outcomes, right? And so there does need to be a human in the loop. We shouldn't just let ASR systems run wild. And in fact, this is something that I think broadly the US government is thinking about as well, right? So thinking about live captioning. So this ties in directly to YouTube specifically. Thinking about things like the New York City hiring laws. And so ASRs are actually a huge component of that as well, because video interviews are becoming a huge thing where effectively there's a standard slate of questions and you record yourself answering these standard slates of questions. Increasingly, the video is no longer being used thanks to papers like Gender Shades. but a lot of the audio is still being used. And so you can imagine all of the huge issues there, and just perpetuating biases. And so having some type of auditing, regardless of whether it's the kind of auditing that's indicated in this law or not, is broadly going to be kind of a really important step going forward. And so broadly, lots of work to do, lots of anxieties about the world. And I'll just leave you all with this open question of, we clearly have to figure out what's fair here, but who really should be deciding what's fair? I think this is just a really important thing to keep in mind going forward in terms of figuring out what should our ground truth be, how should we be thinking about things like hiring or court reporting or things like that. And with that, I'm happy to stop for questions. And if you want to play around more with any of those scatter plots where you could click on the dots and listen to people's ASR transcriptions and look at the tagged grammatical and phonological features, fairspeech.stanford.edu is where you want to go. So we have all sorts of fun interactive things going on there. All right, thank you so much.
So I'm gonna thank Allison on behalf of everybody for a wonderful talk. And let's open it up for questions. So, as usual, just feel free to unmute yourself and ask a question, or if you prefer, type it in the chat. I'd also just like to particularly encourage students to feel comfortable asking questions. Otherwise, I'm going to ask questions.
Go for it.
Okay, so I'll ask the first question. So I am curious, do you know if any follow-up study has been done more recently? Like, is this still, when this came out, there was a big splash, right? And so I'm thinking with gender shades, it's like all these companies kind of, very quickly fixed the underlying issue, at least in their, if you ran the same kind of test that gender shades did now, you wouldn't see those kinds of disparities, presumably. Do you know, did something similar happen with the 5 companies that you audited?
So I would say it's a lot trickier to solve this question because the data collection step is actually much more time intensive. So while these companies have broadly improved, I would say actually the kind of new interesting thing is a lot of smaller startups, smaller ASR startups, have launched products specifically marketing themselves as fairer, better at different kind of sub-dialects of speech, that sort of thing. So, they may not have as much, they may not have nearly as big a corpus as these big tech companies in terms of just kind of general standard American English, but they do outperform on a lot of metrics for all of the kind of sub-regional dialects or varieties of English that you might think about. The interesting thing with the big tech companies is, of course, you have to spend a ton of money to find people to interview. Then you have to get a bunch of hardworking linguistics grad students to then transcribe everything so you have some ground truth, and then, yada, yada. So it's just a much longer process. So I would expect that we'll see improvements on kind of a longer time scale relative to things like gender shades.
Other questions from anybody?
I have a question. Oh, sorry. Tara wants to go. I see her hand is raised.
Marley, why don't you go first, and then Tara afterwards, if that's okay?
Okay, great. Thanks. Hi, Dr. Koenecke. I'm sorry, I was late. My question about your work is, has anyone from these major companies, have they reached out to you to critique the work? And have they given any response, or are they just letting this kind of like float out there without acknowledging it?
It's a great question. Definitely no one critiqued our work because I think they all recognized that it was clearly an issue that none of them had invested the resources into training on more diverse data. So from what I can tell, the response was broadly like, I guess this is a thing we need to do. And I think broadly it was useful to shine a light on for them, because oftentimes it's very easy to think, well, we're a big tech company. A lot of them have phones, right? And so a lot of the phone users will use these speech-to-text systems. And so you get this nice feedback loop of, you continuously produce new data. You have a new stream of training data that you can use because your users are going to continuously use your product and make it better. But maybe what was being overlooked was the fact that clearly for a subset of speakers, for example, African-American English speakers or non-native speakers, they might use the speech-to-text feature once on their phone and realize it doesn't work and then just never use it again. And so this kind of breakage in this feedback loop was perhaps something that just no one ever highlighted. And so it wasn't clear that, you know, a huge investment in this kind of like training data collection needed to be done. So hopefully, fingers crossed, things are changing now.
Great, thank you.
Tara, do you want to go next?
Sure, thanks. I'll just give the disclaimer that I'm a linguist, but I really enjoyed hearing this talk engage with concepts from linguistics and sociolinguistics. My doc student, who's a sociolinguist, had to leave and go teach, but we both really appreciate the collaboration with linguistics and the serious thought that's going into this. I just had a couple questions. I was curious about how the errors were being computed, or just the nature of the errors that were being detected. The first one was, to find the word error rate, it seems like you're trying to find the alignment between two strings. And I was curious if there's an issue with propagating errors if you miss a deletion or an insertion, and then everything after that will be flagged as a substitution when actually there's a way to optimize the alignment that reduces the error rate. Is there something built in to correct for that?
Great question. So we do alignment based on timestamps, and we did a lot of manual cleaning to make sure that the timestamps were aligned specifically to avoid this issue.
Timestamps at the word level.
Sorry, no, timestamps for each turn of speech. So again, we're segmenting to 5 to 50 second snippets for each speaker. So just be when the interviewer starts speaking until when the interviewee starts speaking to when the interviewer starts speaking. So we have that range of timestamps to segment the audio wave files. And then we also had timestamped ground truth transcriptions. And so we were able to match at the, I guess we did have it by the word, or at least by the utterance level, for what timestamps were for each of those words. So we were able to align them pretty well. There were some minor cases of just errors in some of the transcriptions, but we cleaned those manually.
Got it. My other question was the nature of the errors that you see. Was there a tendency for the model to sort of standardize the types of the grammar? So for example, if somebody said he walked using African-American English, would it hypercorrect that to he walks, and then that would be an error? It's a different word, but it doesn't change the meaning. So did it sort of tend to standardize the grammar that was being used?
A great question. I believe the answer is yes, but we never actually did a thorough kind of full review of all of the errors because there were too many errors to do this on. But at least just kind of pulling out examples, it did seem to be on average that might happen. But also there are many instances of just kind of like random words and gibberish that were being inserted and things like that.
Thanks. Great talk. I appreciate it.
Thank you.
Can I just quickly ask a question about the word error rate? I mean, is it possible to have a word error rate bigger than 1 if there's a lot of what is it, like insertions, like just lots of words that never appeared? Is that possible?
Yep, it is possible. We very rarely see word error rates more than like 70-ish% in practice. Okay. But again, depending on like what ASR model you're using, if it's kind of a less modern one, you can end up with issues like that.
Thanks. Other questions from anybody? Looks like Soumya wrote a question in the chat. I'll just read it out loud for everybody's benefit. Hello, thanks for your presentation. You mentioned that lexicon was not indicative of racial bias, but the transcriptions that we heard sounded like they misheard many of the words with regards to African-American English. I was a bit confused about this difference, and maybe I missed something.
Okay, super helpful question. So one example that we heard a lot, for example, was with our white speakers. A lot of them lived in Humboldt, California, and often they would talk about where they were from, because this is part of the standard slate of interview questions, and it would get transcribed as the word Humboldt, Humbled, instead of Humboldt, the city. However, we know for a fact that Google and Microsoft, etc., actually do know the fact that Humboldt, Humboldt, does exist as a word, because it did successfully transcribe Humboldt as Humboldt a few times, but also mistranscribed it as Humboldt a few times, right? And so in that sense, we knew for a fact that the city name was in the lexicon, despite the fact that there were a lot of mistranscriptions of it. But for a lot of other words, you might be worried that, for example, if a lot of people were talking about, for example, the local indigenous peoples, tribes that were local to their areas. And a lot of those words, it was unclear to us if they were in the Google lexicon, for example, because we never saw an instance of it ever being correctly used in the ground truth. And so that was an issue that we were worried about if we weren't sure that it actually fundamentally existed in the lexicon. Whereas with a lot of the mistranscriptions, yes, they were mistranscribed and like clearly mistranscribed much worse for African-American English speakers relative to white speakers. But for a lot of them, we were able to tie back to the fact that, in fact, these words definitely did exist in the lexicon because they were, at least at one point in time, transcribed correctly, or even mistranscribed in that maybe someone was talking about feeling humbled, Humbled, and it was mistranscribed as Humboldt. So as long as we can tell that Google knows that the word Humboldt, the city name, exists, then we wouldn't consider that as something missing from the lexicon. Does that make sense? Great. Great question.
Other questions? Okay, I'm going to ask another one then. So I was curious, I know in other contexts in algorithmic fairness, there's a whole proliferation of various metrics, right, for measuring sort of inaccuracies and disparities. And I'm curious, not really knowing anything about linguistics, word error rate seems very natural to me as the measure of disparity. But I was curious, are there other ways to think about measuring errors in these kinds of systems? And was there sort of a discussion of like there are these 3 different ways that we might reasonably measure error rates across races, let's go with word error rate, or is this like pretty much the standard thing that everybody does in the field?
For sure, great question, and kind of both. So word error rate is kind of the standard thing that people use in the field, but there is kind of like this whole spectrum where maybe actually the thing you care about is character error rate and not word error rate. So like, why have we decided that the word is the important thing? Maybe actually we care about misspelling or like adding an S or taking away an S, right? Something like that. You can also zoom all the way out into what's called a paraphrase error rate, right? And this is actually something that is done with the final example with court reporters, where it was found that they were much worse at transcribing African-American English speakers. It turns out that even for African-American court reporters who speak African-American English, they also weren't able to meet the bar at transcribing African-American English speakers in court, similar to their white counterparts, the white court transcribers. So both of them did poorly on the word error rate metric. However, if you ask them to paraphrase what's being said, the African-American English court reporters far exceeded the white court reporters, right? So this takes a lot more kind of human time. There isn't an easy way to kind of numerically turn this into a metric necessarily. But zooming out and figuring out, like, can you paraphrase what this person is saying and actually get the gist of what they're trying to say correct? That is kind of what we ideally want to do, but very hard to do in terms of like a numeric optimization, right? So word error rate is kind of this like nice middle ground. And oftentimes it's also useful to report kind of the individual breakdowns of like the substitution error rate and the deletion error rate and the insertion error rate. So broadly, people use word error rate. Unclear if it corresponds to what we actually want to measure, which I think is something closer to paraphrase error rate. But here we are.
Thanks, that makes a lot of sense. All right, anybody else?
Hi, yeah, I had a question. In your talk, you were mentioning, I guess, evaluating the acoustic models kind of separately from the large language models, and I was wondering if there were any issues that you saw with that and any biases that could amplify by not evaluating the, I guess, the acoustic plus large language models as a system.
It's a great question, and a lot of it was just trying to tease apart this kind of like, well, if we had read speech, wouldn't it be cool that we could see this thing? In reality, a lot of these language models are these end-to-end models, and it's not like they necessarily have 2 totally separate components that are then like, first you do the acoustic, then you do the language. It's not like that anymore. It maybe used to be, but at this point, they're just kind of like massive neural architectures that are very intertwined. And so we saw this kind of like 3-point testing sort of thing, mostly as a way to tease apart, well, if we actually had read speech, would we be able to find these clear differences? And less of maybe like, if we were to isolate just the acoustic model part, which seems kind of like a fraught activity because, you know, these language models, or sorry, these ASR models are so complex, and it's not like there's just one tiny separate bit of it that's the acoustic model, and it really does work quite hand in hand with the language models at this point. So this is kind of the best we can do to tease out that effect. But definitely happy to chat if you have ideas on how to think more about kind of the interactions between acoustic and language models.
Thank you. Yeah, I think if we evaluated the entire thing as a system, I guess even for your work, we wouldn't have been able to figure out that the issues weren't necessarily from the large language model. And I wonder if that could propagate even now, evaluating the system as a whole, that you wouldn't know that the issue is with the intonation and not necessarily with the language aspect of it.
Right. For sure. And I guess one other thing I'll say is I think this is really important because a lot of the call to action is like throw more data at the thing. But actually, a lot of it does need to do with making the acoustic model better in terms of the actual modeling. And one kind of big example here is with male speakers. One of the kind of the first plot that I showed that was like, oh, this is what the media reports on. I totally glossed over this. But if you look at it, men's word error rates are consistently worse than women's error rates. And this is not because there are no men in the training sample. As it turns out, men are perfectly well represented in the training data. Most likely this happens because men tend to, on average, speak with more disfluencies. And so this would be more like saying things like or maybe taking a bit more time to say things and doing so at kind of different rates. So these disfluencies are things that acoustic models are just really bad at picking up on and transcribing correctly. And so that's a place where it's like, oh, you should probably figure out how to actually model this correctly acoustically, because clearly throwing more data at the thing is not working. So that's kind of one example of why it's important to think about this as maybe separate things. Yeah, hopefully that's helpful.
All right, so in the interest of time, I think we'll end here. So I'm going to just thank Allison again on behalf of everybody for a really wonderful talk. Yeah, thanks everybody for joining us. And you can see our slate of upcoming talks on our webpage. We have some good ones, some more good ones remaining this semester. So hope to see some of you there.
Great. Thank you so much, everyone.